The principle of conservation of energy is one of the most powerful and important ideas in all of physics, with implications, both fundamental and applied, throughout the sciences and engineering. We are first exposed to this principle in the context of mechanical energy. In this mini-lesson, we will briefly review the principle of conservation of mechanical energy and the concepts that underlie it, and then we will work through an example to demonstrate how this principle can be applied to solve physics problems. This approach will frequently be the easiest route, and sometimes the only route, to solving problems. We begin with a brief review. The forces that we encounter in mechanics problems can be sorted into two categories: conservative and non-conservative. A particular force is said to be conservative if the work it does on an object moving between 2 points depends only on the starting and ending points and not on the path taken between them. Two examples of conservative forces that we encounter frequently in mechanics are the gravitational force and the restoring force of an ideal spring. The expressions for the work done by these two forces has been derived elsewhere and is merely presented here. Notice that in both cases, the work done by the force does indeed only depend on the initial and final positions of the object. If negative work is done in going from the initial configuration to the final configuration, it is always possible, with a conservative force, to do the exact same amount of positive work by returning to the initial configuration. So whatever kinetic energy was lost in doing the negative work in the forward process is regained in full in the reverse process. This suggests that energy has been stored in the forward process and extracted in the reverse process. This stored energy is called potential energy, and a key characteristic of conservative forces is that there is always a potential energy associated with them, such that the work done by the force is minus the change in potential energy. Why minus? Well, if the force does positive work, then by the work kinetic energy theorem, the kinetic energy increases. That should correspond to a decrease in potential energy. Similarly, if the force does negative work, kinetic energy decreases, and therefore the potential energy increases. The expressions for the work done by gravity or an ideal spring suggest the form of their potential energy. In particular, the gravitational potential energy of an object of mass m at vertical position y is mgy. And the elastic potential energy of a spring of stiffness k, stretched or compressed by an amount delta s, is 1/2 k delta s squared. If the only forces that do work in a given system are conservative forces, then the system is called isolated. Non-conservative forces may be present in an isolated system as, say, forces of constraint, provided that they do not do any work. We call the sum of the kinetic and potential energy of all objects in a system the total mechanical energy of the system, and we designate it by capital E. The principle of conservation of mechanical energy states that for an isolated system, the total mechanical energy is constant. Energy can change its form from kinetic to potential, from potential to kinetic, from one type of potential energy to another, and so on, but the total energy does not change. This is described mathematically by the equation E equals a constant, or equivalently, if in a problem there is an initial event and a final event, then the total final energy, K sub final plus U sub final, equals the total initial energy, K sub initial plus U sub initial. Let's do an example to see how this is used in practice. Two objects are connected by a massless string passing over a massless, frictionless pulley, as shown in the figure. Object A is released from rest. Use conservation of mechanical energy to answer the following questions. A. What is the speed of object B the instant object A hits the ground? And B. How high above the ground does object B go before momentarily stopping? The question we need to answer first, however, is, does conservation of energy apply in this problem? Well, there are two forces in this problem, gravity and tension. Gravity is a conservative force. Tension, on the other hand, is a non-conservative force. However, the work it does on object A is the negative of the work it does on object B. So the tension does no net work. Since the only force contributing to the total work on the system is conservative, the system is isolated, and therefore energy is indeed conserved. Let's first compute the speed of object B the instant object A hits the ground. Since mechanical energy is conserved, this computation is quite straightforward. Both objects start from rest, so they both have zero initial kinetic energy. If we choose ground level to be y equals 0, then object B has zero initial gravitational potential energy, while A has gravitational potential energy m sub A times g times h. Therefore, the total mechanical energy of the system at its starting point is E sub I equals m sub A times g times h. Throughout the motion, the downward velocity of A is equal to the upward velocity of B. That's because the string connecting them remains taut. Let's call their common speed just before A hits the ground v. Then A has final kinetic energy 1/2 m sub A times v squared, and B has final kinetic energy 1/2 m sub B times v squared. Since A is now at ground level, its potential energy is 0. But B is now at height h, so its potential energy is m sub B times g times h. Putting this all together, the final total mechanical energy of the system is E sub F equals 1/2 times the quantity m sub A plus m sub B times v squared plus m sub B times gh. Since mechanical energy is conserved, E final equals E initial, or 1/2 times the quantity m sub A plus m sub B times v squared plus m sub B gh equals m sub A gh. Solving this equation for v gives v equals the square root of 2 times the quantity m sub A minus m sub B times g times h all over m sub A plus m sub B. Plugging in numbers and evaluating, we find the final speed of both objects, A and B, to be 4.43 meters per second. Since B still has kinetic energy, it will continue to rise even after A has hit the ground, converting kinetic energy into gravitational potential energy until all its kinetic energy is gone, at least momentarily. For this part of the motion, A is no longer involved, so the mechanical energy of B is conserved. It starts with kinetic energy 1/2 m sub B times v squared, where we figured out v in part A, and with potential energy m sub B times g times h. So the initial mechanical energy of this part is E sub I equals 1/2 m sub B times v squared plus m sub b times gh. When b reaches its maximum height, it's momentarily at rest, so its final kinetic energy is 0. Its final potential energy is m sub b times g times h max, where h max is what we're trying to calculate. Therefore, the final mechanical energy is E sub f equals m sub b times g times h sub max. Since the mechanical energy of B is conserved in this part of the problem, its E final equals its E initial, or m sub b times g times h max equals 1/2 m sub b v squared plus m sub b gh. And solving for h max gives h max equals v squared over 2g plus h. And plugging in numbers and evaluating, we find that B reaches a maximum height of 5.0 meters.